Hi, this is Mrs. Villette, and this video is on Riemann Sums. It should correspond to your section 5.3 notes, and this part of the video actually starts on the second page of the notes. I chose to do a video on this part because this first part is fairly easy. It's mostly some basic arithmetic, and I want to save the more difficult thing with sigma notation for what we do in class. So we're going to talk about approximating techniques for finding the area under a function where we can't use geometry. So for example, we've got a parabola here, and I don't have a geometric formula for how to find the area under a parabola. Now the actual parabola is given by x squared plus 1. So we are going to approximate the area using the indicated technique. We're going to go over a few different techniques. One technique that is never really discussed is you could just count boxes. So you could just count how many boxes and kind of approximate where you have half boxes and full boxes. But we're going to instead use rectangles. So in part A, we're going to be using 4 equal width rectangles whose heights are the y values on the right end points of the rectangles. So I can see if I'm going from 0 to 2, and I was going to do equal width rectangles, the width, which we're going to call delta x, would be the length of the interval, 2 minus 0 divided by 4, or 1/2. You can already see that I've got markings every half unit on this graph, and so here are going to be the sides of my rectangles. Now I want the heights to be the y values on the right end point. So my first rectangle I'm going to make with the height at the right end point. So I'm just extending across, and we can clearly see that this is going to be a huge overestimate. If I look at the areas of each of these rectangles, there's a whole bunch of area that goes above the curve. Now we go to actually finding our approximation. The best thing I found to do is to make a chart of x versus f of x values. So my first endpoint is 0.5, and then I have 1, and then 1.5, and then 2. My function value at 0.5 is 0.5 squared plus 1, or 1.25. And then at 1, we're at 2. At 1.5, we're at 2.25 plus 1, or 3.25. And at 2, we are at 5. Now the area of each of these rectangles is going to be, so the area of each of our rectangles is going to be the base times the height. Well, the base is always going to be delta x, and the height is going to be the f of x at that particular place. Now since I'm going to have equal width rectangles and there's 4 of them, the easiest thing to do is probably to just go ahead and total up these function values, because I'm going to add up all my areas. And when I total those up, I get a total of 9.5, and then I'm going to multiply that by 0.5. So the area total of the rectangles is 0.5 times 9.5, or 4.75. So my approximate area is 4.75, which is a way over approximation. Okay, so now we're going to do the same thing using 4 rectangles and left endpoints. So I've drawn my rectangles, and each one of them, the height is found at the left end point instead of the right end point. So it's a very similar table to what I had before, except now our sample points are 0, 0.5, 1, and 1.5. 0, we're at 1, and then we're at 1.25, and then 2, and 3.25. Doing the same thing that we did before, we're going to do the base times the height and add those all up, but it's actually a little bit faster if we just add up all the heights first. And when we do that, we get 7.5. So our total area of our rectangles is 1/2 of 7.5, or 3.75. So our approximate area is 3.75, and that is clearly an under approximation because we can see that we are missing some pretty big, almost triangular shaped regions by doing these right endpoints. Let's try for a better approximation. A better approximation might be to kind of combine the right and left endpoints, and instead of doing a rectangle, doing a trapezoid. So we can see how this trapezoid is sketched here. We'll go ahead and fill in the other trapezoids as well. And that looks much better in terms of how approximations go. The thing that we need to remember is that the area of a trapezoid is 1/2 the sum of the two bases times the height. Well, in this case, the height, we're actually thinking of this trapezoid as being on its side, is going to be the delta x. So we're considering the height, even though it's not really height, to be this distance between the bases. And then we are going to add up the side length. So I'm going to call this like x sub I and x sub I minus 1 to indicate that they are the adjacent endpoints. So let's go ahead and get the table we had from last time, except now we need all of the function values because we need both the left and the right endpoint of each one. I'm going to do the trapezoid for each region. So my trapezoid area between 0 and 0.5, I am going to do 1/2. I'm going to add the bases, so 2.25, and then I'm also going to multiply by delta x, which is again 1/2. The next one, I'm going to do 1/2 of 3.25, so sum of the bases times the height, which is 1/2, and then 1/2 of 5.25, and then we're going to do 1/2 of 8.25. Now you might notice that in each one of these I'm multiplying by 1/4, and then I could just add up all of those numbers that I have in the middle. So add up all of these. And those middle numbers add up to 19, so I end up with 19 over 4, or 4.75. Okay, now if we look carefully, we can see that each trapezoid does go slightly above the parabola, so this is still an over approximation. One thing that I hope that you noticed is that our right approximation was 5.75, and our left approximation was 3.75, and our trapezoid approximation is 4.75, which looks to be the average of the left and right approximations. And that should always be the case, that the trapezoid approximations are equivalent to doing the right and the left and then averaging them. So the last one that we're going to do on this video is midpoints. And a lot of people think that midpoints and trapezoids are the same, but they are not unless the function is linear. So I'm still going to do 4 regions. So my 4 regions still have the same endpoints. But I'm going to construct my triangle where the height is at the midpoint of each region. So you can see that my rectangle here has a little bit of an over approximation on the left side of it, but an under approximation on the right side of it. This is going to be a little bit harder to tell whether we have an over approximation or an under approximation. We're going to have to set up our table in a similar manner, except now my sample points are going to be 0.25, 0.75, 1.25, and 1.75. And then we calculate our function value. It's probably actually easier to do this in fraction form instead. So 1/4 squared plus 1 is a 16th plus 1, or 17/16, and so on. So I'll go ahead and fill in the rest of the values. Okay, so here are our function values at the sample points. And again, I'm going to add these up. This adds up to 148/16, so that's adding up the heights. And if I want to get the area of the rectangles, I'm going to do the sum of the heights multiplied by the width, and the width is still 1/2. This ends up being 37/8, or 4.625. Okay, so is this an over approximation or an under approximation? I probably should have been a little bit better about drawing my midpoints here. Let's look at one that looks like it's drawn pretty well. So this one, I can see that the amount of area that I'm missing, this little triangular region here, seems to be bigger than the amount of area that I am compensating for on the other side. And a similar thing goes here. I'm going to guess that this is an under approximation. And again, if I had drawn a little bit better picture, maybe used a straight edge, I could have been more sure of myself. Now what we'll do in class next time is we'll go look at this on a computer applet and we'll figure out what the actual value is, and then we'll be able to tell for sure if it's over or under. So that's it for the video. It's mostly just finding function values, adding them up, multiplying by the widths. The only one that wasn't that simple was just the trapezoids, so finding the area of a bunch of different trapezoids.